This lesson is about sequences. The word sequence is used in mathematics in much the same way it is used in ordinary English. If someone heard a sequence of bad songs, you know that person could list the first bad song he or she heard and the second one, and so on. So a sequence is a type of list. The first type of sequence we will explore is an infinite sequence. An infinite sequence is a function whose domain is the set of positive integers. The function values are written as a sub 1, comma, a sub 2, comma, a sub 3, and so on toward infinity. If we are discussing a random element in this sequence, we would call it a sub n, indicating we're not exactly sure where the term falls in the sequence. Each of these values, separated by commas, are referred to as the terms of the sequence. The nth term, a sub n, is called the general term of the sequence. 0 can also be used instead of 1 as the first subscript, and the sequence can be written as a sub 0, comma, a sub 1, comma, a sub 2, and so on. If the domain of the function consists only of the first n positive integers, the sequence is called a finite sequence. So an infinite sequence will continue on toward infinity, and a finite sequence is countable, meaning there's a certain number of terms and that's it. So just keep in mind that sometimes a sequence will begin with a sub 1 and sometimes it will begin with a sub 0, depending upon the context. I know from experience that there are many computer programming languages that will address sequences where the first term is the 0th term. So just be flexible there. We will generally use a sub 1 to be the first term. So we're going to look specifically at implicitly defined sequences. Implicitly defined sequences have a formula that we can follow. And here you see several examples. And it's really nice to just see a bunch of different type of examples of sequences so that you can later write your own formulas given a specific sequence. In each of these examples, it says write the first 4 terms of each sequence. And we're given the general term of a sub n equals 5n minus 1 for the first example. This simply means if we want to know the first term, we will substitute 1 in place of n. If we want to know the second term, we'll substitute 2 in place of n, and so on. So you can see that we've done that. We've substituted 1, 2, 3, and 4 to find a sub 1, a sub 2, a sub 3, and a sub 4, or the first, second, third, and fourth term in this sequence. Now, these are infinite sequences, meaning we could continue on toward infinity, but of course that would not be practical, so we're simply listing the first 4 terms. All right, you see in the second example, we have a formula, a sub n equals 1 over n plus 1. We substitute 1, 2, 3, and 4 to obtain the sequence 1/2, comma 1/3, comma 1/4, comma 1/5, and of course, that sequence would continue on toward infinity as well. Remember to place commas between the terms in a sequence. All right, you see the next example, a sub n equals negative 2 to the power of n. So this time you're substituting 1, 2, 3, and 4 as an exponent. It's very important to note on this one a very common mistake that students might make. If we follow order of operations in this third example, the exponent must be applied before the negative sign. So this says the negative of, or the opposite of, 2 to the power of n. That is why all of your terms are negative, because the negative sign is applied after the exponent. If the negative 2 were in parentheses to the power of n, then the entire negative 2 would go to the power of n, and some of these would be positive. The even-powered terms would be positive, because when you take a negative number to an even power, it becomes positive. But that would only be if negative 2 were in parentheses. So just be careful for that. Pause this video if you need to continue with these notes for the first 3 examples. I'm going to go ahead and move this up so you can see the next 2. All right, for this next example, we seem to be missing a squared. This is supposed to say a sub n equals 5n squared minus 1. I'm not sure what happened to my exponent of a 2, so forgive me for that. In the final example, we see that in the numerator we have negative 1 to the power of n. This is a very common practice if you need your terms to alternate signs. So the first term is going to be negative, the second term will be positive, the third term will be negative, the fourth term will be positive, and it will continue alternating positive and negative. So this is a tool that we can use if we need to write an equation for a sequence and we need the signs to alternate. Again, this goes back to what I was saying earlier. If you have a negative quantity in parentheses to the power of n, we know that odd powers of n are going to be negative and even powers of n are going to be positive. All right, so this next part, we're going to be writing, let's see, what does this say? Oh, maybe we're not ready for that yet. It says, frequently the first few terms of a sequence exhibit a pattern that suggests a natural choice for the general term of the sequence. Write the general term a sub n for a sequence whose first 5 terms are given. So this is much more difficult, in my opinion, where you are given the sequence and you have to come up with the formula or the general term that would generate these numbers. You must keep in mind that the numbers that we are substituting in for n are 1, 2, 3, 4, 5, and so on. When we substitute 1, we should get an answer of 1, the first term. When we substitute 2, we should get an answer of 4, the second term. When we substitute 3, we should get an answer of 9. When we substitute 4, we should get an answer of 16, and so on. So notice the pattern suggests that a sub n is simply n squared. When we substitute 1, 1 squared is 1, so that works. When we substitute 2, 2 squared is 4, and so on. So be on the lookout when you're writing a formula for the square numbers or something to that effect. The best way to get good at writing equations such as this for the general term is practice, because you're going to say, I think I've seen a sequence like this before. Let me look back in my notes and see if I can find something similar. Okay, for excuse me, for this one, our first term is 0, our second term is a half, our third term is negative 2/3, and so on. You might notice that we're alternating negative and positive. Of course, negative 0 is just 0. Notice when we plug in the number 1 into our term, we have to get an answer of 0. And when we plug in 1, we have to get an answer of 1/2. And when we plug in 2, we have to get an answer of 2/3. So you might notice that the top number might correspond to, the bottom number corresponds to the value of n. So notice in my formula here, the bottom number is just n. This could be 0 over 1, and then we have 2, 3, 4, 5. The top number is 1 less, so notice n minus 1. The top number is 1 less than the denominator. And then we have our negative 1 to the power of n, which will cause our signs to alternate. So again, as you are working through examples, I would just encourage you to look back at your notes and try to find an example that is similar.